And in reality, people quite often come across so-called multi-stage isothermal sintering. I give an example that I take out from a book. Okay, you see, we have multiple so-called isothermal heating, right? Isothermal hold. But then from room temperature, you heat, hold. The first stage you call it maybe to a low temperature in order to do bundle removal, bundle burnout if you are in air. Okay, and then sometimes you heat up further and hold at another temperature that is lower than your highest sintering temperature. Sometimes you do it for low temperature soak. It's not necessary, but sometimes people do it. And then heat up further to your highest temperature, hold for sintering, cooling down, hold again, sometimes, not always, sometimes hold again for so-called annealing and final heating. Okay, this type of heating schedule, people call them multi-stage, very simple. Okay, and as we explained, quite often the first stage you go to is for bundle organics burnout, because quite often after green body formation, other than dry pressing for those that involve slurry or paste, you add organic bundle, and those organics needs to be removed at temperature below, much lower than sintering, and in a controlled fashion, not causing explosion, because organic burnout is going to relieve water, moisture, water vapor. It's also going to release carbon dioxide, carbon monoxide. All those gas, if you don't release them in a controlled fashion, they may cause so-called explosion or mini explosion, right? Causing weakness in your sample. Okay. Quite often you heat up slowly to a temperature roughly 500-ish for organic burnout. If you are doing this in air. If you're not doing in air, you may have to go a little bit higher. And certain binder people use if you're not using in air. Like for nitrogen, if your material is sensitive to oxidation, you cannot burn out your material in air, then you have to be very, very careful in the choice of your so-called binder. Because some binder, when they burn in inert atmosphere, they don't decompose into small molecules. They leave a lot of so-called residual carbon, which is bad for your material. Okay. So for those types of situations, you say, okay, I cannot use air for burning out. I have to use nitrogen, and then you have to be very, very careful in choosing your binder. Such as, especially, typically people can use small cellulose-based, or not cellulose, the so-called acrylic that decompose completely into small molecule. Those binder that when in inert atmosphere that gives you carbon, like essentially sugar or starch-based, they are not good, because when they decompose in inert atmosphere, they leave a lot of residual carbon, which may not be good for you. Okay. Low temperature soaking, I put that in gray because it's not always happening. It's not always necessary. People do that to carry out certain reaction, to do certain so-called homogenization, make the material composition more homogeneous before we reach high temperature. And typically you do that below the sintering temperature. Okay. And then heat up to the sintering temperature, which is you quite often try to do the fast heating. Quite often, after the organics are gone, you can now heat relatively fast. Fast heating leads quite often, people find they lead to better densification, smaller grain. Okay. And the heating rate limited essentially by your furnace, your material, how much power you have for your furnace, and also what's your conduction mechanism and how much sample you have. And also thermal expansion. For certain material, if you heat up too quickly, especially there are multi-layer material coming together, if you heat up too quickly, the thermal stress may cause so-called delamination. between different layers if your structure has different component, different material within them. Okay, and after that is isothermal sintering, which is here. Isothermal, the highest temperature isothermal sintering, sintering at the same temperature. If your temperature is too low, you may find not adequate sintering. Okay. On the other hand, you also do not want to do sintering at too high temperature. You do not want to ramp up to too high temperature to do sintering, even if your furnace allows them. The optimum is quite often somewhere in between. Too high temperature, what people find is, what happens, it's so-called coarsening. Before sintering, before densification. What is coarsening? Coarsening is essentially particles getting very large. But coarsening can happen without densification, which means the particles are getting larger and larger, but in between the porosity have not been removed. So those are bad, because in the end, you have huge grain, but then I have a lot of porosity in them, which means that mechanical property would not be good. And if you are talking about other property, may also not be good, like electrical or thermal. Okay? So it's always a compromise, not too high, not too low. Okay? And here we're showing the kind of the conceptual idea. Vertical axis is relative density, like from 0 to 1. Of course, quite often we do not start from 0, because when you compact the green body, you start from somewhere around the 55 to 65% relative density. Make sense? You do not start from 0 because you packed already green body together, powder. And then from there, isothermal sintering time. If the temperature is too low, you end up, after a very, very long holding, you still do not reach full density. Make sense? On the other hand, if your temperature is too high, it initially increases very fast, but kind of saturate still at a certain location, because the particles are already too big. Meanwhile, you still have a lot of porosity that haven't been removed. And once the particles are very, very big, the surface becomes flat. There's no further driving force for densification to occur. So somewhere in between. Somewhere in between. That's your sweet spot. Okay? After isothermal sintering, sometimes, as we mentioned, there might be an annealing, primarily for mechanical engineer to relieve stress. Sometimes, okay, you hold it when the material is still not fully hardened. That thermal stress can go away by, I don't know, not exactly plastic deformation, but by some internal motion that allows the relief of the stress. Okay? And after that, you cool the sample down. Can be fast if the sample is small. But if the sample is very, very large, quite often be very careful when you cool, because thermal expansion may cause, thermal shrinkage may cause cracking in the sharp corner in locations like that, so-called stress concentration location. Make sense? Because the inside and outside, if you cool too fast, the outside may go very quickly to low temperature, inside is still hot, and that creates a lot of trouble, micro cracks. Okay? Thermal stress and sometimes for precipitation, for phase change. Okay?